So in this video, what we're going to look at is other ways of writing down our solution for a simple harmonic oscillator. We've already seen how we can write it down as a simple cosine function with an amplitude and an initial phase, and now we're going to look at other ways of putting this down in a mathematically equivalent format. Okay, so here we are looking at our mass spring system that we had before. The mass M is resting on a flat horizontal frictionless surface, and it has a spring that generates a force kx. And as we've seen, we have the solution for the position x at time t, and we could write that as a cosine omega t plus phi. And here a was our amplitude, which was the maximum displacement from equilibrium. We had phi as our initial phase, which is determined by where the position of the mass is at time t equals 0. And then omega here was our angular frequency, and omega was given by the square root of k over m. So in other words, the value of this omega depends on how stiff the spring is and how large the mass is. So this is our solution that we derived for our simple harmonic oscillator. However, we don't have to write it just that way. Now, if we noticed here, we had two constants that depended on the initial conditions. We had our amplitude and our initial phase, and those were determined by how we set the spring in motion. This is determined by the spring and the mass itself, and so this is the same for all instances of the motion. The amplitude and the initial phase will vary depending on how you set the spring vibrating. So we're always going to expect to have two constants no matter how we write down our solution. But what we're going to do is remember a trig relationship, which is the cosine of a plus b is equal to the cosine of a times the cosine of b minus the sine of a times the sine of b. And so if I put a constant a in here, then I'm going to have a constant a here and a constant a here, and then of course this I'm going to write as omega t, and this I'm going to write as phi. And if I do that, what I end up with is that our solution is going to be equal to, so this is a cosine omega t plus phi is going to be equal to, and now I've got a cosine omega t times cosine of phi minus a times sine omega t times the sine of phi. And so if I look at these here, this and this combine to give me a constant term of a cos phi, and this and this combine to give me a constant term of a sine phi. So these are going to be two completely independent numbers, right? Because they depend on both a and phi, and so I can choose a and phi to make these two numbers anything I want them to be. So I can rewrite this as a prime cos omega t plus b prime sine omega t. And so this is another way of writing down our solution, and now these are the constants which are determined by how we set the system in motion. And whether it's more convenient to write it down in this form or in the original cosine omega t plus phi form simply depends on the problem that you're dealing with and the information that you've been given. But both of these are mathematically equivalent, and so you can choose whichever one is the best for you. Now, the other thing to remember is another trig identity, which is that the cosine of theta minus pi over 2 is equal to the sine of theta. So if I define phi prime as equal to phi plus pi over 2, then if I rearrange that, that gives me phi is equal to phi prime minus pi over 2. And if I put that into our original solution, then I have a cos omega t plus phi is just equal to a cos omega t plus phi prime minus pi over 2. And so this is just equal to a sine omega t plus phi prime. So what I've shown here is that by simply changing the initial phase, I can choose whether I use sine or cosine. So again, I can write this down as sine with a phase, and it's just going to depend on what the problem is as to whether it's more convenient to write sine or more convenient to write cosine. Typically, the way we start these problems is you have the mass and it is displaced. If this is the equilibrium, you start with it displaced at the amplitude, so x is equal to a, and the velocity of the mass, so that's x dot, is equal to 0. And that's typically how we start these problems. And so in that case then, you're better using the cosine, because the phase then is equal to 0, and so that's why we want to do things typically with the cosine. But you're free to use sine if you want. You just have to have a different value for the initial phase. Now there is another way that we can write down our solution, and that is, if you remember, we started with x of t is equal to a cosine omega t plus phi. And we can write that by saying this is the real part of a times e to the I omega t plus phi. And if you remember, this expands out to be cosine plus I sine. And so we're taking the real part, we just get rid of that, and we're back to this cosine term. And so that, of course, then is equal to this. Now, unfortunately, in physics, we're often a little bit tricky, and we will actually write it as just e to the I omega t plus phi. And here there is an implicit real operator, but we don't often write it down. Now that is bad mathematically speaking, but that often happens because we use this form particularly when dealing with quantum mechanics, when we actually worry about the imaginary part. Now, the reason that that's dangerous is because certain operations that we will do on this displacement, you have to remember that there is this real operator in here. So to give you an example, if I want to differentiate it, right, so I want to take dx by dt, then this works fine even if I forget that there's the implicit real operator here. And the reason for that is if I take something like a plus ib and I differentiate it, I get dA by dt plus I dB by dt. So if I've forgotten about the fact that this term really isn't there, it doesn't matter, because the real term I'm left with only depends on the real term that I started with. So I can take the real operator here after doing my operation, and I'll still get the same result, right? So here I actually should not be differentiating the I times b, because it's not really there, because I've taken this real part only, so I've only got a, and so the only term that I should be left with is dA by dt. But as you see, if I take the real part, I'll get rid of that term, and I'm still left with the same result. So there, it doesn't matter whether we take the real part before we do the operation or after the operation. But suppose I'm interested in x squared. Then I have to remember to take the real part and only square the real part. And the reason for that is a plus ib squared is going to be equal to a squared minus b squared plus 2abi. And so the real part here depends on both the real and imaginary parts of the original expression, but this part isn't here, and so therefore this part shouldn't be here. So here I must take the real operator before squaring it. Right? I must take the real part only. I can't just square this ignoring the fact that there's an imaginary part here. So you have to be very careful if you're using this expression here, that you remember that you sometimes need to take the real operator, you need to take the real part before you do whatever operation you're interested in. Now, the other thing that's interesting with this way of writing things, though, is that I can simplify things a little bit. So x of t here is equal to a, and I'm going to rewrite it slightly, e to the I phi times e to the I omega t. Now, if I multiply these two terms together, I'm going to get I omega t plus phi. So this is clearly equal to what we started with up here. And now what I can do is I can look at this. Now, a is a real number and phi is a real number, but this is a way that we can use to write any complex number. So let's call this z. And so I can rewrite this now as z e to the I omega t. Now, what I've done here is I've written it down now with what we call a complex amplitude. And the reason that this is interesting is because this complex amplitude, it contains the real amplitude, so I can use this to extract the real amplitude, and it contains the initial phase. So both pieces of the initial information of the oscillator are actually contained in this single complex amplitude. And to extract it, if we go back to here, you can see that, remembering that this is the way, this way of writing down a complex number, that this number here is the modulus, and this number here is the argument. So if I write it down with a complex amplitude, then this real amplitude here is just equal to the modulus of the complex number, and this is just equal to the argument. So I can write down my oscillator just as a simple z e to the I omega t, and that contains all the information about the oscillator, because this complex amplitude contains all the initial conditions, and so that's a simplification of writing down our solution. So now we've seen other ways that we can write down our solution, our displacement, as a function of time for the simple harmonic oscillator. Now, one of the things I promised you early on was that this vertical mass spring system here behaved in exactly the same way as the horizontal mass spring system that we've been using in all of our mathematical examples. So now what we're going to do is we're going to look at this system and show and demonstrate that this also undergoes simple harmonic motion. And so here is a mass spring system in the way that you more normally see them, where the spring now is vertical and the mass is hanging freely beneath it. And so L0 is the natural length of the spring. So this is when there is no external force applied to the spring. And then X here, of course, is the extension of the spring. And here we have our mass m with the weight now hanging vertically to give us a force downwards of mg, and upwards we have the spring providing a force upwards of k times x. So we can now write down Newton's second law for this system. And of course, since we know this system oscillates, we're expecting to get something that looks like our simple harmonic oscillator problem. So let's have a look at this. Well, what we've got acting downwards in the positive direction, so we're going to take downwards as positive. Then we're going to have mg minus k times x, so that's the net force acting downwards. And this is going to be equal to the mass times the acceleration, and we're going to use Newton's dot notation, so x double dot. So if we rearrange this now, we're going to have x double dot is going to be equal to minus k over m times x. But now we have this extra term plus g. And so this is not exactly the same. Remember, we had the original equation of motion looked like this. We had x double dot was equal to minus k over m times x. And so the problem we've got is we've got this extra g term here, which is going to mess things up, and we're not going to have the solutions to this equation look anything like the solutions to this equation. So the question is how do we make this look more like this, right? This is what we want it to look like, but we've got this extra g. So if you remember before, we had x as the displacement from equilibrium. So this was the displacement from the equilibrium position. Here, though, we've defined it as the extension of the spring. Now, in the case where the spring is resting on this flat horizontal surface, the displacement from equilibrium is equal to the extension of the spring. But here, it isn't. So what we're going to do is we're going to introduce a new quantity. So here we have now the same diagram. We've got the same mass m, but we've split the displacement up slightly. And so what we have here is this is the natural length, right? So this is the unstretched position here. So that's the spring with no force added onto it. This position here, though, now is equal to the equilibrium position. So this is where, if we just had the mass staying at rest, it would extend this spring by a distance x0. So in the equilibrium position, what we have is we have the force on the spring, so that will be k times x naught, is going to be equal to the weight of the mass, which is just m times g. So this is the condition for equilibrium. Okay, so here we have our condition for equilibrium. So now we've got a new variable here, which is the displacement from the equilibrium position. So let's write down Newton's second law here. Right? And we're acting downwards. So as positive. So what we've got is we've got mg, that's the weight, and then we've got minus kx. And x now is x prime plus x0. This is the total extension of the spring. And this now is going to be equal to m, and so it's going to be the rate of change of this total displacement here. So this is going to be m times d2 by dt squared of x prime plus x0. But this is a constant, so when we differentiate it we get 0, so this is just equal to m times x prime double dot, because this disappears when we differentiate it because it's a constant value. So rewriting this now, we'll bring it down here. Rewriting this, we're going to have mg minus kx prime minus kx naught is equal to mx double dot prime. But our equilibrium condition here says that these two things are equal. Right? These two expressions here are the same. So we've got mg minus kx naught, so this and this cancel, and what we're left with is x double dot prime is equal to minus k over m times x prime. And this is exactly what we had before, and so clearly we have simple harmonic motion. Right? The difference is that for simple harmonic motion to work and to get an equation of motion that we can easily solve because we've seen it before, we must use the displacement from the equilibrium position. So whatever type of simple harmonic motion you are dealing with, you must always use the displacement from the equilibrium position. Otherwise you get these constant terms, as we saw before, that will make the equation of motion impossible, or at least a lot harder to solve. Obviously you can solve it and you will get the same answer, but it's going to be a lot more challenging than if you just use the displacement from the equilibrium position. So always make sure you're using that when you're applying these Newton's second law to these oscillating systems. So now we can show that this behaves and undergoes simple harmonic motion in just the same way as our horizontal mass spring system. But there's one final type of solution to the simple harmonic oscillator which we're going to look at, and for that we're going to reintroduce complex numbers and have a look at the vector that results in a complex plane. So let's now return to the way we had of writing our solution, x of t here, as a complex number, e to the I omega t plus phi. Now, of course, we're with here. This has been the implicit real. But let's now just look at this solution here, and let's draw this on an Argon diagram. So the reason for doing this will become clear in a minute, but of course, even though we're drawing this on the Argon diagram, we're only ever going to be interested in the real component of our solution. So if we draw it on the Argon diagram, we remember that we can write any complex number as some a constant here, let's call it b, times e to the I theta, where b here is the modulus, and theta here is the argument. And what that looks like, if we draw it on our Argon diagram, is we have the imaginary axis here as the y-axis, we have the real axis here, and so if we're drawing this complex number here z, remember that the argument is this angle here theta, and the modulus is the length of the line from the origin to the point that represents this complex number. So if we look at this now, and we go back to our solution, what's this going to look like on an Argon diagram? Well, here we have our imaginary axis. Let's add our real axis along here. And so at this point here, we can draw our line out from the origin. And the angle here is going to be omega t plus phi. And the length here is going to be a. This is the amplitude. So we've got a line whose length is given by the amplitude of the oscillations, and we've got an angle here that's given by omega t plus phi. So as t increases, this means that the angle, right, or our argument, will increase. So what that means is that this line is actually going to move round with time. So to see that better, let's have a look at a slightly neater diagram. And so here we can see this line, and so this here is the initial position. So this is where our line starts when t equals 0. And as time increases, this angle here between our initial condition, our initial line, and where we currently are is going to increase. So this is going to move round, and what we've done is we've converted our oscillator, which goes backwards and forwards in the real plane, into circular motion. So now if we look at this solution in the complex plane, then the length of the line is going to give us the amplitude. So as this line goes round the circle, the radius of the circle is going to give us the amplitude of the oscillation, and the position here will give us the actual physical position at any one time. So if I'm here at some time, t prime here, all I have to do to find my my real position is I just look at this distance here, right? So this is the real displacement. So by projecting this circular motion and only looking at the real component, what we've seen is that there's a clear link between the circular motion of something and an oscillation. Because if we look at our solution in the complex plane, we end up with a circular, something that's moving in a circle, versus what we have in real life, which is this thing that's oscillating backwards and forwards, because we only see the real component of this solution. So what we call this line here is, it looks a little bit like a vector. We call this a phasor, right? Which is essentially a vector in our complex plane, but the only part of the phasor that we see is the real component of this phasor, right? But essentially it gives us the phase of the oscillation, and so that's why the initial line here is determined by phi, which of course is the initial phase of the oscillation. So you can see that there's a clear link between the circular motion and the oscillator motion. So let's see if we can actually bring this to life and do a demonstration which shows this link very, very clearly. Okay, so what we saw mathematically was that when we had our complex solution to the simple harmonic oscillator, it looked like circular motion. So what I've got here is I've got a ball that's attached to the arm of a motor that will go round, and the motor will drive this round in a circle, and next to it here I've got the ball, identical ball, on the end of a mass spring system. And the frequency of the motor and the characteristics of the spring and the mass have been tuned so that they go round at the same frequency. So if I get the timing of this correct, what you will see is you will see these two objects move up and down apparently in sync, and yet this one is moving round in a circle and this one is moving up and down. So I'll turn the motor on and we'll give it a go. So here you can see the two objects oscillating apparently in sync. Of course, from your point of view with the camera, you can't see the circular motion. Essentially, we're projecting out the imaginary axis. So in this case, the imaginary axis is this one that gets nearer to you and further away from you, and the real axis is the one that goes up and down, and that's what you see. So mathematically, the motion of an object going round with a uniform angular velocity in a circle is the same as the object moving up and down undergoing simple harmonic motion. And just to show you that this object really is going round in a circle, I'll slowly rotate this round so that you can see that you do indeed have this object going round in a circle while this one on the mass on the spring is just going up and down. So the two types of motion really are equivalent. Now, as a last word before we move on to another topic, make sure that you spell Phasor correctly. The type that you're going to be using in your exam, I hope, is spelt with an O. You do not want to be spelling it with an E, because that means something entirely different. So please remember, when you're doing physics, use an O for Phasor. So we've now seen how the displacement for a simple harmonic oscillator can be described by a rotating vector in a complex plane. In the next video, we're going to see how this explanation can also be extended to the velocity and the acceleration of the mass, and so we end up with three different types of phasor. So until the next video, live long and prosper.